Questa è quella che di fare qualcosa. Vediamo? Che se lo diamo fuori, guarda, se ti prendo cosa ne vediamo. No, probabilmente ti blastava di prima. Secondo me non sparava. No, ma è un cazzotto, legale. Il suo nick si chiama Cosmologico. È la mossa del One Piece. Esatto.
Okay, so welcome everyone. I hope you all had a nice trip to Trieste and you found your way and everything else. So I hope you're gonna have a nice time during this workshop. Maybe before we actually start this off, just a couple of things. So as you notice, we're gonna have the coffee break upstairs in this very building, but the cafeteria where we're going to have lunch is at a different building, it's at ICTP, so we're going to go to the ICTP cafeteria. So maybe for the first day we can just, like, after the first talk, we can all meet outside this building and we can go together, so we show you the way. And then to enter the ICTP you will need the ICTP badge that you hopefully have found. If you don't have it already, you will find it, so you have to go to the ICTP main entrance, but this week, and they will give you, but this weekend you can talk to me if you don't find a way. And that's it. So just come to us if you have any questions regarding the organization of everything else. Now I will leave the floor to Robin, which will chair the first session of the day.
Yes, and also to say welcome everyone. The afternoon talk will be at 2:30 and then there will be another coffee break after. But now we're happy to start with Alessio, who will be telling us about Regge's Inferno.
Thank you very much, Robin, and thank you, Stockman and Robin, for organizing this very nice conference. So I'm very happy to start it today. And what I will present is this paper, which is appearing very soon with Zork, Mazowski, and Pedro Pupol. So the idea is actually, so I know that this is a conference on the holography. So this is more on the dual side, so this is more about safety, but I will comment on holography more towards the end of the talk. Please, if you have any question at any point of the talk, also the talk is Blackboard, so it's very helpful if you ask questions during the talk. So let me start by a very brief motivation. So we want to understand CFT, and when we want to understand CFT, it means that we want to understand the spectrum of operators. So we want to understand how essentially the density of state is made on CFT, which essentially means that we want to understand where operators are and how they are characterized in terms of the conformal dimension, the spins, which may be more than one, and then the charge if there are some global symmetries. And an equivalent way of saying this is that we want to understand some partition function in which we compute the trace. Usually we use some notation of this style. And having the spectrum is essentially equivalent of knowing this function as a function of beta, epsilon mu, beta if you want to take this temperature, epsilon mu or something else like this. So what is known about the spectrum of those operators? So if all the charges, so the conformal dimension, the spins, and the charges are small enough, today we have very good numerical techniques to compute essentially spectral operators, which is like conformal bootstrap, or more precisely the numerical conformal bootstrap, which curve out the space of those operators, in particular when all these numbers, quantum numbers, are essentially very small. But okay, if the light operators are somehow under control, what about the asymptotic? So, or if you want, what about the heavy states? So what we can say about them? Of course, it's very hard in general to count one by one. So what we will do is essentially to compute some average density of states. So we want to understand how the density of states behave essentially when this at least one of these numbers is very large. And probably what you know better is the Carty formula, which was already proposed in 2D many years ago. I think is some reference there, I think number 2, and then extended by Shagulian and then by Simon Duffin and the Caltech group, actually only a few years ago. I apologize, I think after chatting with Shiasim and Val, I think I should put also some reference to his papers, but I didn't do on time. That was a recent conversation, but anyway, in the last, I would say, 10 years, we also understand how to generalize them. And since some technique will be similar, let me just schematically review how to get this in higher dimension. And for most of the talk, I will talk about 2 plus 1 dimension, and then also 2 3 plus 1 dimension. So when I will not specify in my mind, it will be 2 plus 1 dimension. And the simplest thing you can do is to essentially use the fact that the free energy, if you want, is just the integral over the space, the spatial, the 2-dimensional space, and then some coefficient plus correction. So what is this? So essentially, this equation just means that if you have some like spatial geometry and the temperature is high enough, you essentially, if you want the thermal circle is so small that you don't care about the spatial geometry, will just enter in a volume factor, and this is just the thermal free energy of infinite volume. And then this correction will essentially know about the precise space, the precise geometry in the spatial directions. And if you just Laplace transform this equation, what you will find is essentially what we call the Cauchy formula, which is the fact that log of rho is essentially this coefficient f times delta to the power 2 over 3 if we are in 2 plus 1 dimension. So the argument is as simple as this, and as you see, it essentially use, if you want locality, because you essentially need to factor out the volume, and very few ingredients, if you want. It's just an EFT at high temperature. So that's the only things I need to get this Cauchy formula. And this was also analyzed in 4 dimension and so on. And it's extremely simple. So this is the simplest thing you can do, and this coincides essentially to take in this partition function epsilon and mu equal to 0. So which means that we don't really care about the spin of the operator, we don't care about the charge of the operator, we just average over everything, and we only care about the conformal dimension. In fact, where it's not refined in spin and it's not refined in charge. But of course, you can do better than this. Okay, or maybe make the translate something. You can do better than this, and you can refine it. And for instance, you can ask what happens if the charge is very big. So if the charge is very big, there are actually quite a lot of paper. I will use this paper, which is from Gabriel Cuomo and Zorko Markowski in 2022. And well, one of the possible results you can get is that the dimension in this case grows as 3 or q to the power 3 over 2. This essentially will take care of beta, epsilon, mu, if you want that. Well, it essentially is defining all the fugacities. But actually it's more complicated than it is, because you will have actually more than one phase. In particular, if you put spin and you put q, depending on how the charge scale with the spin, you will have different phases, and the conformal dimension will grow in slightly different way. So this is another possibility that you can do to understand the density of states and how the scaling dimension grow. But what we are interested in this talk is another limit, and essentially the limit. So today, what we want to understand is to understand the limit in which mu is 0. So we'll average over all possible charges. I will not care about global symmetry, but I will keep epsilon. Actually, we'll keep epsilon equals to 0. I will show you later why. Because essentially, well, the simple way to say that is that this is going, j goes to infinity. So what I want to understand is essentially what happens to the density of states when we want to look at very high spin. And of course, high spin, even just intuitively, or if you want semi-classically, you can understand that this is also high dimension, right? Because you expect that at least classically the dimension goes with the spin. So this is what we will study today.
Very stupid question.
Yeah.
In the larger scale, do you have also mu to be small, but doesn't scale with that? Like,
Well, no, actually I just simplified a lot because I mean there are other regimes in which I don't remember all the regimes. I think there is, for instance, one regime in which Q is from J and J is 1/2, and then there is some. If you just Laplace transform, there is some.
some error between mu
Yeah.
and epsilon.
Yeah, exactly.
While here you want to put them both to 0 the same way, or?
No, mu is 0 from the beginning, and epsilon will be a
okay.
limit. I will show you in a
Okay,
second.
okay.
Yeah.
And the central charge is fixed.
Well, depends what do you mean with what is the central charge for you here. Look, here we are in higher dimension. So if you want, what for me would be the natural place for the central charge is this F, which is actually the free energy of the system at infinite volume, which in 2D is differential charge, but it doesn't coincide with CT. And this for me is just a parameter, of the theory.
So the question is, it's not scaling, right? You don't, when you take...
No, a large charge it just happens that it doesn't. But you will see, well, the Cardi formula I showed you before scale with this F, like the Cardi formula in 2-dimensional scale with C. In large spin, I will show you that this F will enter again. But that it doesn't, I think the interpretation why it doesn't scale with F is just because you can understand that result in particular. It's just like computing the, well, if you are a large charge, essentially you can understand it on the sphere, so in radial quantization you will have like a uniform distribution. So that's just the density of the uniform distribution on the sphere. So there is not much that you are inputting to it. Okay, more questions? So what is known about this limit we want to take? So what is known about the operators in spin and twist, where the twist is delta minus J. Let me say in 2 plus 1 dimension. In 2 plus 1 dimension, the rank of SO3 is 1, which essentially means that I only care about one spin, one object, which I will call it JZ if you want. I will, if it's not clear, we'll define it later directly on the sphere, but I mean, it's just because the rank of SO3 is 1. And what we know here, so as I said before, if these quantum numbers are small, here we have numerical bootstrap, and this we can compute it numerically. We also know something else. We know that if the twist is small enough, this is what people call the Regge theory. Sometimes people also call the light cone regime. I will use Regge because I'm more used to this, but if you are more familiar with light cone, just translate it to light cone. And here what happens is essentially that it's semi-classical. So take, for instance, operator in the theory that classically looks like this, for instance. Well, this operator will have dimensions that are 2 delta phi plus L, and then correction. And this correction, well, are order of 1 over L. Actually, maybe L to some power. I will not give you so much details. This depends essentially on how the minimal twist goes in the crossing equation, if you want. So it is the power is actually the minimal twist of the theory. Usually it's 1 because well, I will not give you so much detail. If you want, it's a scientific answer. Yeah, I will not comment so much about this. But please ask me questions if you want me to do this. Okay, so there is still an infinite space that we cannot cover here, which is all the theory essentially in which the twist is large enough with respect to the spin. And I will show you today some result that will go essentially in a region which essentially interpolate between the Regge theory, and this is essentially when tau is going to the square root of Jz, and I will tell you what is tau that's scalar the square root of Jz, why this is nice scaling. And I will show you actually that there is well, the odd space-time of the title is essentially a PP wave, which you may be familiar, or maybe not. If not, I will explain what a PP wave is. So the main claim that I hope I will convince you of during the talk is that you can essentially understand the density of states of the CFT by placing the theory of the CFT directly on a proper PP wave. Okay, so are there questions? Otherwise I will start going slightly more.
Maybe just a maybe question about terminology. So we already call Regge theory when this Jz is bigger than 1, not necessarily much bigger than 1, or
Well,
eventually it's going to be much bigger than 1.
yeah,
Okay.
usually this
Oh,
is
okay.
what I mean
Okay,
by
okay.
Regge theory. But you're actually right, it's not extremely well defined. The best definition I know is comes from inversion formula. And there is a moment in which essentially large spin perturbation theory, which is what you get from inversion formula, will break down. When this happens, I would say that it's no more Regge theory. However, in realistic theory, for instance, I don't know, 3Dism, this happens to be spin 2, spin 4, so it's not that high.
2 is big.
Right. Of course, the more you are going to low spin, the bigger is your anomalous dimension. But this doesn't mean that the perturbation theory is wrong, is not working anymore. Okay, so let me start by doing the simplest thing. Let me try to compute something slightly simpler, or at least that it seems slightly simpler, which is something of this type. So what happens if I try to compute this partition function? So this actually will directly diverge, and it's so simple to see. It's just because if you take this operator, so just descendant on some primary, let me take the primary to be a scalar, it doesn't change nothing if it's not a scalar. Well, this is a kind of one particle partition function, and this is E beta tau of phi, and then there is the sum over 1, essentially, because you see the twist of these operators, L phi, is simply, if you want, this delta phi plus L, but then we subtract back L. So it's essentially the dimension delta phi. So this means that all these operators have the same factor here. So they essentially, it's just the sum of 1, and this diverges, of course. So instead of doing this, what we need to do is one with like a small perturbation around this. And in this context, now epsilon will go to 0. And in this way, I will regularize this because this will be beta epsilon L. And indeed, now this is just a simple sum. Beta epsilon. So you see that this will regularize essentially this sum. And in fact, there are actually rigorous theorems on this, which were already from the Weidmann axioms in 89, which is reference 8. And reference 8 tells us that essentially for epsilon goes to 0, this partition function will converge. But in any case, we actually not even on CFT. But in when epsilon goes to 0, instead, what you expect is essentially what I just showed you, that the partition function will diverge. And notice that I show you something about descendants. You may ask if this is just a descendant degeneracy, so it's something that you can cure by quotienting out the descendants, but that's clearly not, because if I compute these operators, these are all primaries and are semi-classical, as I told you before, so this partition function will diverge in any case. So this means that there is no hope. This partition function will have divergence, so we have to deal with it, and this indeed, if you expand this, you will see that this is 1 over epsilon divergent. And so what we actually want to see is the divergent, and is the coefficient, is the residue, essentially, in front of the divergence. So what we can say here about this? So, as I said before, when the twist is small enough, what you have is essentially just what I wrote here. So here I almost already did the calculation, you just have to adapt it with these kind of operators. And what you will find here is that the log of z, in this case, will be 1 over beta epsilon, and then some simple exponential of this type, where tau 0 is the minimal twist in theory. Essentially, it's exactly the computation I just carried out there. Well, if you want, this is not that crazy, right? Because this is if you want a low temperature computation, if you Laplace transform, this is e to the minus beta, the minimal energy. Remember that our energy is essentially delta minus j, which is the twist. So this is something that you can guess essentially from the beginning. What about high temperature? Well, we do exactly what I showed you in the Cardi formula. So what you will do is to say that the log of z is essentially again the same. Minus 1 x f and you can Laplace transform this equation, and what you will get is that, sorry, I messed up with it. This is log of rho, so let's plot the constitute state, and this grows as f over beta squared epsilon. So you see now at high temperature instead is very important this coefficient, which is the thermal free energy of the theory, and as in the Hadi formula, it's important to know exactly what this is from. Okay, so what you can do now is to essentially look these two equations and say, well, so let's assume, and I will show you later an argument for that, but for the moment let's assume that the log of z will indeed be beta epsilon. I will use conventionally factor to pi, you will understand why, but it's not important, it's a factor. And then some function of beta. And this function of beta is the one that goes to these two limits in the high and small temperature. And you Laplace transform by adding beta tau, beta epsilon jz. And when you Laplace transform, what you will get is a very nice equation. Rho tau in jz is essentially the square root of jz, and then a Laplace transform in the variable tau over square root of jz. And okay, let me just say, if you Laplace transform in the two limit, this f tilde will go, so in the beta goes to infinity, the low temperature, this will be 2 tau over tau minimum, square root of jz, and the log of tau minimum, square root of jz over tau, and in the beta goes to 0 limit, which is the high temperature limit, you will have 3f to the power 1 3, and then tau over square root of jz. So, okay, this is a guess. If you want, I will show you later why this guess is actually nice. But I have to also to say that this was already conjectured and perturbatively proved, and the perturbation is in high temperature in a very nice paper by Shiraz Minwal and his collaborators, which is reference 9. So this perturbatively was already known, so it's not a random guess. I will show you now a non-perturbative proof of this. And this Laplace transform is done at beta fixed, which is, what if you do the computation, I'm not doing it, it's quite straightforward, is essentially translating over square root of jz fixed, and epsilon goes to 0 is jz equals to infinity. So this is essentially the regime I'm looking at. Okay, so
basically, you started by regularizing the partition function by adding an epsilon times jz.
yeah.
You got the first result that is perturbative in epsilon, this one?
No, that's so that's a guess. What I get is actually the two limits by the low temperature and high temperature, and this was instead a guess just by looking at that. But if you want this perturbative to in another paper by Shiraz Minwal.
Okay, so like the final expression holds when epsilon goes to 0, but jz, this means that jz is going to infinity.
Yeah, yeah, if you want, okay, here I'm putting 1 over epsilon. Of course, here there will be order, well, regular term in epsilon, which I'm just subtracting away. I'm just looking the straight jz to infinity. Okay, so the two questions that I want to answer today are the following. So the first question is, let's look at this equation here. So this equation should look very familiar because this is some kind of a thermodynamical equation of this type, where the entropy is equal to the volume, so it's just the fact that the entropy is extensive. The entropy is equal to the volume times some entropy density in the energy density over the volume, the energy density, right? So this is a kind of extensibility of the entropy. So this equation looks very much this one. So the first question is, where does this kind of very nice thermodynamic interpretation comes from? If it exists one, and I show you that it exists one. And the other question I want to answer is, okay, we have these two limits. So how we compute this f practically? So is there a way to define this f non-perturbatively? And also to this, the answer would be yes, and I will show you that actually the method to get the answer is essentially the same. So we just have to understand better, essentially, these limits. Okay, so is the question clear? From now on, I think I will just answer the questions.
You're always working as CFTs.
Yeah. I think in the paper of Shiraz there is also a test in some massive free theory, and it seems to work the same, but what I will show you now is very much less effective. You will see in a couple of minutes. Actually now, because I will put some operator that looks like this, so I will put like a bunch of operators. So this is my operator at large spin that I want to study, some operator of this kind, classical of course. And I want to put this operator in radial quantization. So I want to understand what happens if I put this operator in radial quantization. I mean, you understand that I can split this in blocks, and these are like particles moving very fast because the spin is very fast, so the momentum is very high in radial quantization on the sphere. And the dimension, delta, is a sum over the spin, and then n delta 0, well delta 0 is actually delta phi, let me give you delta phi, and then some anomalous dimension. Well, the first thing we want to understand is the following. So you know that there are two ways to break perturbation theory. One is when the coupling is too big. The other way is when the external leg are too much. And so the first thing, since we are looking at a lot of these operators here, the first thing I should show you is when this is well defined and when this is not well defined, when this perturbation theory makes sense. And let's just estimate this anomalous dimension. Well, that's, I mean, I think the intuitive thing is that this is a two-body problem, a two-body interaction, right? And indeed, I mean, this grows as n squared over j pi, right? Each of these interactions grows like this, where n squared just comes, if you want, by the counting n over 2. So that's just the limit of n over 2. And I may statistically say that each of these L, if you, oh sorry, I changed the notation, J1. These Ji are just essentially the total spin over n. This is, of course, doesn't have to be, but statistically this will be true, right? And you just plug this back, and what we get is that this grows as n cubed over j. And if you compare this with essentially the classical part, what you will get is that this is a good approximation when n cubed over j is less than 1. Which, if you want, if you compare, n grows with tau, j is j. So this is essentially when tau over square root of jz is much less than 1. So we already answered a small question, which is where this tau over square root of j come from. So this is not a random scaling. It's exactly the correct scale that essentially regulate when the breakdown of the EFT will be. So,
did you explain from this picture why the gamma is proportional to 1 over j and not to 1 over j to some power?
Right. So that's a very good question. If you want, here I'm just using that there is this is the locality. There is a stress tensor, and I'm assuming there is no scalar below this threshold.
Okay.
That's one way. Another way is that I'm actually cheating because I'm doing like this small computation. Actually, conceptually is not even completely correct because these particles are very fast moving, but this computation is for slowly moving particles. However, we are quite lucky because this result is actually correct and was checked by Peter Kravchuk and Jeremy Mann in a paper where they did the full computation in the EFT, and they show you that essentially the correct variable is always tau over square root of jz. Incredibly, this is true in, I would say, any dimension, but I think they check only in 3 and 4 dimension. And this is always the scalar of breakdown, which is very beautiful for me because it explains very nicely why this scale appears naturally here. But it's perfectly true. I'm cheating. This is just a scaling computation, and is actually quite wrong if you try to do it correctly. I just wanted to give you an idea of why the scale emerged. If you try, for instance, to reproduce in 4 dimensions, you will find some obstacle. And the reason is that this computation is not completely correct, but it was done.
Sorry, just to make sure I understood. So did you say the power does not depend on the space-time dimension?
No.
So it's not related to power.
Well, yeah, to be honest, here I should put tau minimum. But it happens that, they find that essentially the fact that they are moving very fast essentially make this dependence tau minimum go away. It's a quite tedious and very long computation, but it was done explicitly. But yeah, it is remarkable that it does not depend on the dimension of the space-time. But it will depend, so until now I've only put it one spin. In 4 dimension you will have the rank of SO4 is 2, so you will have J1 and J2, right? And that will change. If you keep both of them open, I will show you later, but if you keep both of them open, this scale will change. But if you shut down one, so if you only keep one open, so only one very large and the other one order 1, you will always get this. I think the reference, if you really want, is reference 10 is this paper that I mentioned. Okay,
Sorry,
so
Alessio, can you just repeat how you lost from n to the power of 3 to n squared when it 1 power?
oh, you have to compare with n.
Ah, okay, good.
So you just okay. Okay, so we just understand where this scale comes from. Now let's look a bit closer. And let's look to the wave function of these particles moving there. That's very simple because it boils down to a harmonic oscillator. I will show you lots of harmonic oscillators in this case. And what happens is when J is very big, this will be T phi Jz, and then some sine J theta. And this is actually the wave function of this object, and if you just look it carefully when J is very big, what you will find is that this is essentially all localized around the equator, as you actually can imagine. I think it's quite intuitive, right? Spinning particles in a sphere stay on the equator. But what tells us better is that delta theta is the square, so 1 over j to the power of minus 1 half. If you want, it's like a Gaussian. So this is the sigma of the Gaussian, it's the variance of the Gaussian. So this means that all the physics will be captured in a small region here, where this is epsilon, square root of epsilon, which is 1 over square root of jz, if you want. And all the particles will move very fast around this. So this is essentially the motion we want to study. So they will move very fast in the equator, and they will only explore a small region statistically. So what we can do now is to zoom in this specific region. And if you know the Penrose limit, which from where they come the PP wave, that's exactly what Penrose did many years ago, kind of. And in fact, we will get it. So let me do it explicitly. So the metric of the sphere is just this one, beta square plus sine square theta d phi square. Right? This is the metric of the sphere. But because we are looking at large spin, if you want, because there is a, sorry, I move it, remember the partition function minus beta h minus 1 minus epsilon jz. Remember this. So because we have beta both here and here, essentially the phi direction, which is the one that defines jz, is periodic, not in the usual way into pi, but it's periodic in beta. So this means that it's much easier if you make the identification disappear by rescaling phi essentially in this way. I think I mess up some sign, probably here minus here is a minus. And what happens, okay, I'm basis, we'll cancel here and put here 1 minus epsilon d square. So this is actually this kind of squash sphere we want to study, and this capture is a kind of commuting coordinate, if you want, for these particles moving on the equator. And now let's finally take the limit to zoom in this region. So the limit is essentially the following. So we will take theta around the equator with the variance of epsilon, and then let's call this variable y. And just to make the final result better, I will put the square root of 2 here. The square root of 2 doesn't have any meaning, it's just to make it more nice at the end of the computation. Phi will be like this because I'm on the particle. Imagine I'm following this particle from inside, and then P is just P. You do this change of transformation, and what you will get, what you will get is that ds squared is, well, let me write it one time explicitly. 1 plus y squared dt squared dy squared dt dx. And then there are higher order in epsilon. So this is the kind of things that you get at first order in epsilon. I'm in SFT, I'm allowed to build, transform away this object here, and so here. And essentially this is the metric I want to follow. Let me forget about higher order in times. In epsilon, this is the metric I want to see. So,
What's the last term? DT?
so this is dt dx.
What's X?
X is, oh sorry, I called y dx. That is meant to be x. Sorry, thank you. Okay, so this is the final geometry. How many of you already saw something like this? Just to, you were, okay. Well, many of you didn't saw this kind of metric. Let me say what it is. This is called Brinkmann EP wave.
So, but just before we zoomed in on the wave function of the entire set of particles or just one of them?
The entire.
The entire thing. Okay, so this is supposed to capture the whole band and not just a particular. Okay.
Yeah. If you are familiar with that, this is literally a Penrose limit in which you sit on the graviton at the speed of light. Sorry, the photon, the speed of light. Okay, so this is what the metric is called Brinkmann PD wave. I don't know if that sounds. What is more interesting for me is that there are some symmetries, and in particular, you can define. Yeah, okay. Let me go very fast in this, but I can define some symmetry with K1 as a given. Well, yeah. The isometry is essentially defined by this given vector K1, which is the x. K2 is less trivial, but you can check that this is an isometry dx, and K3 sine p dy minus y dx. And the commutator, well, I can even rephrase this by choosing this coordinate, and this will give you the only non-trivial commutator being k plus k minus equal to I k1. So if that is not clear to you, don't worry. But the important thing for me is that this commutator looks very like the one of the Heisenberg group in quantum mechanics. Indeed, this group of isometry is H3, where H3 stands for Heisenberg free because there are essentially free generators. So this is great, but I mean, when we find this result, we were a bit puzzled, and we were puzzled because, as I told you before, we want to define thermodynamics here, right? But this is a bit strange because this spacetime is not static, which, if you want, means that you cannot synchronize clocks here. And this is a bit weird because we cannot define a spatial slice in these geometries. So what is thermodynamics in this kind of spaces? So let me make a very small detour in this direction. So I think I will just rewrite almost that in a slightly different coordinates, slightly more general. So this is the most general static, non-static, sorry, spacetime, stationary or non-static. Now, I'm not using the letters randomly because this may be more familiar to you as like electromagnetic field. And this is just what I would call physically the spatial dimension. In fact, I mean, in general, you should also put like here a factor in front, but since we are in CFT, I can always remove it by Fourier transform. So I can simplify CFT my problem. Actually, we find that this is a null problem in mathematical literature to define what the spatial volume means in these geometries. And the answer is not clear. It is clear only when you specify which type of problem you want to say. But physical instead, as I just told you, is much simpler. So that's because I can just recognize that this is a kind of electromagnetic field. Sorry, I put too much. I put too much inside. This is just an electromagnetic field, and this is what I would call the spatial volume. And in fact, this is what happens if you take a reduce, for instance. If you take a reduce, what happens is essentially that the base that you want to write is just Hij, the psi Fj, and then we also discovered that this was not, we were not the first, of course, thinking this problem. And as far as we know, the first person that tried this was Van Dau. And actually didn't want to do thermodynamics, but he asked the following question. So how can I measure here distances? And to answer this question, what he did is the following experiment, well, dot experiment, which is to essentially take two geodesics with xy constant. These are geodesics when n is equal to 1. And let me call A and B, send a light signal that immediately reflect back. You can use that d square is equal to 0, and you can essentially measure the length, and you will discover very easily that it's essentially only generated by this. And this AI are just an electromagnetic field on it. Okay, so that's great, because now we have a notion of spatial direction. Let me emphasize that this is not a spatial slice, strictly speaking. Is I think in mathematical literature they call the metric on the orbit. Is not very important, but physically I think it's very clear that this is what we want to call it, spatial slice. Okay, now that we know that, I just canceled the PP wave, but now that we know that, the first thing you want to do, and this is another small complicance, is that you want to define a volume here. So the way in which we compute it is just to reduce it, take H, what I call it the H in that metric, and directly compute the volume, which is divergent. But it's not a surprise, because we rescaled in a very specific way. So you have to remember that. And if you remember that and you regularize it, the volume of the space is this, that's 2 pi over epsilon. If you want, comes from the fact that in principle this direction are uncoupled because of epsilon, but you have to remember this uncoupled because you insert essentially epsilon. And this is why you find 2 pi over epsilon. Okay, so now I'm very happy because I can define extensive properties. So now I have a volume to which I can define my entropy, I can define everything I want, and in fact, the claim, which is essentially what I just derived, is that log of z is the volume that I just defined there, but if you want times beta if you're used to the free energy, and then some energy. And this f is the same f, actually, since I'm changing notation with beta up to factor beta, but it's not that important, equal to the one before. So this essentially computes the residue, because this is 1 over epsilon. So this is essentially the non-perturbative proof of the scaling that I showed you before. That before was just a guess, or if you want was perturbative proof there, that's completely now non-perturbative. And if you want, that's an EFT for this large field.
Beta was power over square root of j, right?
Beta fixed means fixing power square root of j, yeah.
So you already derived before that the factor in front was 2 pi over epsilon, but you didn't know that this was the volume.
Yeah, so the 2 pi I inserted exactly because I knew that it was the volume. The epsilon was derived, and then yeah, here is essentially the definition. Okay, are there questions? I mean, of course, now I can do the same limit as I did before. I will not do it because otherwise I will spend time, but the same limit as before for high temperature, low temperature, directly the previous way. So the EFT I wrote before, where the integral d-1 xf, I can do it here, and you will get exactly the same result for this function of that. So everything will work out very nicely. Let me give you, I think, the only example I will have time to show you, which is just a free scalar in 2 plus 1, free scalar. So, I mean, the simplest thing I can do is to take a single particle here, which is this particle, and I mean, I can compute the one particle partition function, and this is the usual beta n plus 1 half, and then because there is this epsilon, and remember we are actually using jz, there is some weird factor here, some function of epsilon, which is some ratio of sinh. I will not write it explicitly, I think it's not interesting. But what you will get is 2 epsilon beta sinh of beta vector. And then, I mean, once you have the single particle, you can use Boolean for statistics or statistic exponential. I mean, there are many ways to call it the same thing. And you can get essentially the full partition function. Okay, so how this is reproduced from the PP wave equation? Well, what we have to do is to essentially study the partition function on the PP wave. So let me write on the equation of motion, dx squared phi plus 1/4 dy squared phi plus dp dx phi equal to 0. So that's just the Laplacian here, Laplacian phi equal to 0. I mean, usually, when you have a PDE like this, usually you're not really able to solve it, but this one is particularly nice. And if you just manipulate it, it's actually very simple. You will get a central harmonic of this oscillator. And what you will get is that the energy here are simply k plus n plus 1 half. So the single particle partition function is 1 over epsilon beta. But if you want, sorry, let me write it as in volume over 4 pi. And then 1. Let me write it over dk over 2 pi from 0 to infinity, sum over n, e minus beta, k plus n plus 1 half. And if you compute this, you will get precisely the same equation I get there. The volume is the volume that we cancel here, but it's the 1 over epsilon volume. And yeah, that's a straightforward computation. We get precisely the same equation there. Okay, are there questions? How much time I have?
15.
15 minutes, okay. So, let me try. Okay, I will try now to, so this is all for 2 plus 1 dimension. So we explain essentially we get the Cardi-Foglia non-perturbative, and we also get this extensive property which just comes from the extensivity in the PP wave directly. So let me try to generalize in 3 plus 1 dimension.
Just before that, I'm a bit confused. Why are we writing the solutions to the Klein-Gordon equation of this space and not? I thought we were doing quantum mechanics and approximating the wave function.
No, that was on the sphere.
Okay.
You are putting the free scalar direct in the PP wave. So, yeah.
Okay.
So you want to compute the energy.
Okay, so this was an example for a particular theory.
Yeah, that's just free scalar. Yeah.
And k is corresponding to the x direction?
Sorry?
Out of n and k, k is...
Yeah, I skipped the details, but yeah. Yeah, exactly. Okay, so let me go in 3 plus 1. So in 3 plus 1, you have 2 options. The first is to do exactly the same as we did now. Compute this partition function, where you choose one of the 2 spin that you can define, right? You have 2 angles, phi 1, phi 2. You can just twist one of the 2, and you will get J1, for instance, or equivalent to J2. And what you will get is precisely the same PP wave that I showed you before, just with what I called before y, if you want. Now we'll go to sum over I. You can do in any dimension, actually, with x, I. So this is like straightforward. You can check that everything works exactly the same. But slightly more interesting instead is the case in which you put both epsilon 1 and epsilon 2 and then also J2. So that's different from before. And it's different for many reasons. There are conceptual reasons and practical reasons. The main conceptual reason is the following. So you have now your sphere. Unfortunately, my drawing is not the best, but try to imagine it. And now when you fix the relation epsilon 1 over epsilon 2, is like fixing the ratio of J1 or J2 essentially. But now there is a problem that this J1 or J2 is all the particles that constitute my operator, right? So this means that I'm fixing Ji, J1i over sum over I, J2i. Which means the following, that, I mean, of course, if you take one particle and you fix the ratio, you are fixing one angle, right? Imagine, for instance, epsilon 1 equal epsilon 2 is like the symmetric point, so it's like pi over 4, right, in this sphere. So it's something that goes here. Some particle with a specific theta that essentially is symmetric. And you can do this for any value, any ratio. Just tilt it a little bit, this geodesic. But now we are actually fixing the sum over them over the sum over the J2 of the other guy. So this means that the single particle may be in completely different geodesics, right? So this is much harder problem, at least conceptually, but actually it turns out that it's not that complicated, and the solution is just the Penrose limit, just a bit generalized, in the sense that instead of focusing on one geodesics, you focus on a family of geodesics, which are these ones. And what you will get is a new space-time that I will directly now give the result. I think you may probably already understand the logic. And this is of this type. Square theta bar equal 1. Well, yeah. Sorry. I did this on the 2 dt 4 u dt dy plus du square plus dy square, where u and v are related to the angles and y is related to theta. You actually need to mix the two angles, so it's much complicated, the limit, but I mean, just trust me that at the end you get such a space-time. And this is again a PP wave of the same type as before, is again stationary but non-static. All the discussion as before comes out. You can again study here the symmetry, and these are R times H free, and then you can rotate essentially the H free generators, and this gives you an extra SU2. And there is a very big difference here, and the difference is that before I had again an H free symmetry, and the H free symmetry are essentially broken at finite temperature because they don't commute with dt. Here instead, you can essentially carry out the computation and show that H free actually do commute with dt, meaning that H free is preserved at finite temperature. So this means that finite temperature physics here is symmetric under H free. That will actually change completely the physics in this space-time.
So the geometric side, what is the interpretation? Because before you were focusing on a tubular region around the geodesics.
And here, this is called the Penrose limit on a family of geodesics. So
but it's sampling the whole sphere now.
Yeah. So you're actually measuring exactly this. So you're like focusing on a bunch of geodesics, in this one infinite number, weighted correctly of this type. So you're taking all possible geodesics.
So the interpretation is that this metric is close to the original one, only around those geodesics, and then if I somewhere else, it's different.
No, it's just well.
I mean, the Penrose limit is cutting away some information from the original metric, right?
Right. Yeah, if you want, what you said is true, but you have to keep all possible geodesics. So it's like, it seems that you're keeping everything, right? Because it's.
So it's
Essentially, I mean, you keep all the information on the sphere, right? Because it can be any geodesic from the sphere. So,
But there's not a change of parameter of the sphere.
No.
I mean, the symmetry is different, right? So the metric has to be different.
Right.
And there is some.
So there is also, so I didn't say, but of course there are order of epsilon.
Yeah.
So if you keep all order, it will be just a change, of course, according from the sphere, which is different from before. But since we are actually removing this, then you will not just the sphere. This is a different space.
Can you identify a point on the sphere in which the two metrics are different, or maybe it's more complicated than that?
No, it's more complicated than that, yes. Well, if you want, there is no global coordinate, of course, from the sphere to this. Not even with Bailey scaling. Okay. And the okay, I mean, here also you can define a spatial, well, not the spatial slide, but what I defined before. So this metric on orbit. And actually it will be that the metric of orbits is actually just the metric on H free. So the volume is the volume of H free, if you want. This just comes out of the computation, which is again, you can compute it, and this, which is again what you would expect. I didn't show you this in higher dimension, but it's exactly what you would expect. And so again, you can just say that the node of the partition function is beta, the volume of H3, F beta, and you will get Cardi formulas, you will get density of states, exactly as before. Okay, in the last 5 minutes, let me say something even better. This is why I wanted to go for space time. It seems that everything is quite similar, but there is one main difference. I will try to explain in words, but please ask me to need more details. The point is this, that let me here scheme of what I wanted to say. So in 3+1, we wanted to quantize twist of the type delta minus JC, which by unitarity bound is greater than 0, right? In 4+1, you have two options. Either you quantize delta minus J1 or J2, whatever you want, and here there are unitarity bounds for this. But you also have the option of quantizing delta minus J1 minus J2, and this is not positive in principle from unitarity bound. Doesn't exist a unitarity bound bounding from that. If you want the correct unitarity bound, it's something like delta greater than the max of J1 and J2, but not J1 plus J2. So there is no unitarity bound for this. So can we say now something about this directly from the PP wave? And actually the answer is yes, because if you want, this is positivity of energy. So this is essentially energy. So that's the Newtonian. So this is positivity of the Newtonian. Can we prove positivity of the Newtonian? Well, this is slightly hard. Because, I mean, classically, I cancel the geometry, but classically, the Killing vectors of DT is essentially time-like. So classically is positive, but I mean, you know, quantum mechanics can shift your energy and can be negative. However, in the Regge theory, so in the low twist case, if you have, since twist is essentially addictive, is correct?
Additive.
Additive, thank you.
It's also addictive.
Since it's additive at large spin, what happens is that if you have one negative twist, one operator with negative twist, you actually have an infinite number of operators with negative twist and actually arbitrarily negative. So this means that either the Newtonian is bounded from below and is positive, or is unbounded from below. So this means that essentially the existence of a vacuum in the PP wave is equivalent to this statement. And there is even more. It essentially comes from causality. Now, I cancel all geometry, and in any way it would not be easy to see it explicitly. But essentially, the geometry in which I drop out this term and the geometry where I don't drop out the terms are globally equivalent in the sense that there is a global map that maps the two geometries. However, the Hamiltonian is different, as I'm emphasizing. The Hamiltonian is different. But you see that one Hamiltonian differs from the other by adding J2. So essentially, this means that one Hamiltonian, which is the first one, so Hamiltonian, we call this Hamiltonian 1. So Hamiltonian 2 is essentially Hamiltonian 1 minus P, essentially, minus the momentum, which is positive by causality, right? Nothing can go faster than light in general. So essentially, this means that it's normal that you cannot get that from unitarity, because it's not unitarity, it's something more, and comes from locality, because everything here is very local, causality and unitarity all together. And if you combine all this argument, what you will get is indeed positivity in this sense. So this essentially, I don't know if I want to call it proof. I mean, now I'm just saying it works, but it can be a bit better. But I don't know if I want to call it proof. I think the missing point to call it proof is that you should show that SCFT is causal in this geometry. It's not completely clear to me also because usually axiomatic people would say that causality is an axiom. So yeah, I don't know if that's something that you can prove or you just have to axiomatize. But it's very reasonable to assume that the CFT is causal in the geometry, and then this would be a theorem directly. Note that you need locality because, of course, you can construct a simple counterexample by looking up, for instance, free theory with a higher spin, but adding derivatives. But then this just means that you are essentially looking at non-local theories, and you need causality, as I showed you very explicitly. Otherwise, if it's not causal, H minus P may be negative, and then the argument doesn't work. And indeed, there are no counterexamples, but what is more, there was a paper, which is 11 here, which is by Clayford and collaborators, in which they tried to prove that by using ANEC, so energy condition, and they did up to some spin. So they couldn't really conclude the proof by technical points, but they prove it to low spin at least. So this is not completely new relation, but this may be an argument which holds for any spin. So this is like a bonus point that we find when we just carry out this PP wave computation. I think I'm almost over time, but let me give you some, well, I will skip any example for the mention, I will not have time, but let me give you conclusion and some outlooks that I find it nice. So what I really want you to bring home today is that essentially the large spin limit of SFT with Cardi formula, at least for the spectrum, is essentially captured by placing the SFT on the PP wave. So this is something that I really want to emphasize, and this is essentially the message of this paper we are finishing. But of course you can do more. For instance, one thing we are doing now, let me go directly there, is the following. So in principle now we carry out the computation for the free energy, if you want, for the density of states. But the PP wave actually captures all the theory at large spin. So in principle, you can do more. You can, for instance, try compute, let's say, three-point function of a CFT when of like heavy light, but the heavy light, but the heavy is a large spin operator, something of this type. Tau, this should be tau, JZ, operator light, tau, JZ, and this should be equal to the one-point function PP wave, where this is of course in the limit JZ goes to infinity, and tau over square root of JZ is fixed. And of course, this is kind of beta, so this is the final temperature on the PP wave, in the same way we computed here. So this is something that is quite reminiscent to, if you want, of ETH, in the sense that ETH is the statement that an heavy operator, but if you substitute here heavy operators, this is the same in the flat space, right? And this is a kind of refined ETH in this sense. Of course, ETH also have correction. And this is what is not clear for the moment. But this is a question mark for now. But we already performed this computation. We have already general asymptotics for Clipper function, and we match it in simple theory like theory. Of course, this is very hard to compute in general. The second things we may want to do is to understand like other theories on PP wave. Say, for instance, when model large N seems very simple, is actually not very simple in the PP wave because the sigma field is not constant. So you need a way to compute it, which is most probably numerical. And the last thing, then I will finish, is essentially the question of understanding even better this F function that I defined. So remember log in 3 dimensions, for instance, log rho, okay, is some kind of square root of j, and then there is field of tau square root of j. Now, what about the properties, the analytic property of this F? So in simple theory like the one we saw, it's completely analytical. But in principle, this F should know about like the breakdown of, for instance, perturbation theory, which answer some question of you before, like where is the Regge theory? So this should answer because I expect here some singularity when the semi-classical limit doesn't work. Of course, we carry out a free theory, so semi-classical works everywhere because this theory is classical. We also make an epsilon expansion computation, but also there is perturbative, so you will never see a singularity. However, in the paper of Minwal and his collaborators, they also compute holographically, for instance, n equal to 4. And n equal to 4 has 3 different phases, which are essentially dual to black hole, gas of graviton, sorry, before the gray galaxies, and then the gas of graviton. And so these 3 phases, in principle, are separated by some phase transition, so some non-elasticity of F. And you may ask if this happens in other theory, for instance, say 3Dism. Is there phase transition yes or no. Of course, we don't have a complete answer. Most probably, the first transition here is just a large general artifact. It will not happen in the finite time theories. And in fact, here the essentially tau square root of G, well, for dimension, the equivalent of tau square root of J for dimension grows as n. So you may be tempted to say that this is a large general artifact, but it may be that there is another transition which is more similar to this one. Of course, we don't know yet, but this is something that is very promising, and I think it would be very important to understand the phases at large spin of CFTs. And I think I conclude here. Thank you very much.
Okay, thank you very much. Are there more questions for Alessio?
Maybe I wanted to elaborate on this very latest point you raised. Yeah. So if I understand correctly, there you are thinking about applying what you said to n equal 4 superior means?
Well, it's a bit hard to apply directly for me. What you can do is look the holographic dual. And if you look the holographic dual, there are 3 different phases around spin.
So maybe, let me just say, because that's what exactly, so because on the holographic side there has been this, there was this whole discussion about PP weight limit of n equals 4.
All right.
But that's on the holographic side. I understand you were instead taking the CFT and putting the CFT. So is there any relation between your PP way of the CFT and the PP way that Bernstein Maldacena?
There is, but it's not carried out. So there is actually a paper by Martelli, Tachikawa, and Maldacena. And there, it seems that there is some quite explicit relation in the sense that they see that. I mean, you may ask, okay, you may ask the following question. So I have some CFT on some space. What is the holographic dual of this? And it's not completely clear that it's a PT wave, right? It may be something else. We actually tried to get the simplest answer, which is do the same limit directly, but it's not that trivial because essentially the internal coordinate of ADS should scale with epsilon. So the simplest thing just doesn't solve the Einstein equation. So that is not the answer. But I think in this paper they may have some answer which is relatively close, and you see kind of PP wave. Is not the usual one of the BMN paper. This is another PP wave, but yes, there should be. But then I'm a bit puzzled because I mean, for instance, takes n equal to 4. We know that they have 3 phases, and in the dual geometry we understand this because there is a temperature, and I can vary the temperature, and eventually I would expect to see a different phases, something like the usual black hole thermal ADS transition, right? But in the PP wave, instead, I don't expect that in the dual PP wave. So this would mean for me that we are missing some geometries, even though that geometry may work. It's probably just the class of graviton, but it will.
That geometry, you mean the one of Martelli?
Yeah, exactly. I think they also have some geometry that looks like a black hole. So I didn't check, but I would associate it with a black hole. But I think that the gray galaxy is missing in this computation. But it's normal because I think the gray galaxy only appeared in literature a few years ago in Walla. So I would say for the holographic dual we are missing a lot of information.
But isn't the classical BMN first with respect to the R charge? So in some sense it's a very different type of computation from the CFT point of view. Like
yeah, in that original paper I agree.
Yes,
but you can do it the same.
But then also, correct me if I'm wrong, but I thought that there's also an order of limits where you first take n to infinity and then you look at states with very large R charge, but still one that doesn't scale like n, so you wouldn't expect to capture anything that's related to black holes or
yeah, exactly. Only the class of graviton. Yeah.
Yes.
Yeah, I agree. But instead, this paper, the other paper I mentioned, have a black hole phase. They don't actually do so much. They just show the method. I would associate it to the black hole phase. I think no one checked. As far as I know, I don't know all the literature in that field, but as far as I know, no one checked this. And but it would be interesting to see it. Yeah.
Maybe also more of a curiosity. So in this last case that you were mentioning, you were sending epsilon 1 and epsilon 2 to 0 at the same rate.
Yeah. Yes. Exactly.
Can you send only 1 to 0 between the other one finite?
Oh yes, is what I mentioned. You can just switch off 1 to 2, but what you will get is essentially a 3-dimensional case.
But you cannot keep it finite.
You mean?
Like
Well, but that is like switching off. Yeah, I mean you can, but it's not the last thing then.
And you would have only one of the two atoms.
Yeah, exactly. Exactly. But yeah, I wouldn't expect. I mean, I would expect that the geometry already captured this. You just have to twist it with respect to a finite epsilon.
So I was just wondering, maybe it's like if you set epsilon, say you set epsilon to 0, and you look at small epsilon 1, then you would get something like 1 over epsilon 1. So this would be basically identical to the 3D case. And then if you send both to 0 the same rate, you get something like 1 over epsilon 1 epsilon 2.
Yeah.
So there must be some transition between the two limits.
There must be a transition. Yeah.
Well, because you cannot. I mean, if you send them both to 0 the same rate, you can then you don't recover the other result by then setting epsilon to 0.
Right.
Which
yeah, I
seems
agree.
quite similar to what the Ray galaxy is doing actually.
Yeah, yeah, yeah. I would have said, yeah, probably there is some transition in the middle. I don't know if that's a ordinary limit though. Maybe that is just an ordinary limit. But yeah, I mean, the geometry, the 3D geometry extending to 4D already captures the finite epsilon, right? It's just particle on the equator, and then if you switch on epsilon, it's like slightly bumped in the other direction. But yeah, but still on the equator, right?
Maybe. So initially we started from the question of what's the, well, from a picture where we have a bunch of particles rotating, and then we went to this, then we zoomed in on the equator where this particle rotate, and we approximated the wave function, and that gave us this PP wave limit. But along the way we sort of lost the fact that these were individual particles, which tracked how many, like which multi-twist object we're looking at. Is there a way to reproduce it from this limit, like asking whether for a specific energy, the thing that dominates is something with, which is, I don't know, a double twist or a triple twist or whatever, a 17 twist operator? Or is it completely lost?
No, it's lost. Right, so, no, you are to smear overall. I mean, it depends a bit what you, of course, when you are sending this to 0, of course the minimal twist will dominate. But when this is finite, you have to smear around that. It's more similar to like a statistical smearing about some tau over JZ. So it's not that obvious. It's not that obvious that there is like a single microstate or a family of microstates that completely capture that. On the other side, that's also true in if you take the Cardi formula. I mean, it's very hard to find. In 2D sometimes happens, but in IoT, I think there is no example of like a single microstate capture or the family of microstate capture the Cardi formula completely. And you really need to smear over them.
Yeah, but there are still many multi-twist operators. It's just a question of how many particles do you have on average. Like it could be a statistical distribution, but for a particular energy, it could be the triple twist dominate, and for another, it could be the
well, tau square root of j is fixed, right? So j is to infinity. So tau is to infinity. So I mean, the answer would be infinity, but that's not a great answer, right?
Okay. Perhaps we stop there, and let's thank Alessio again for our So now we'll head to ICTT to have lunch in the
Can we leave our things here?
You can close the, you can push close the class.